Okay, guys, so I totally found another related race one that I missed the first time around, and that was number 16 in your new packet. In the right triangle with a hypotenuse of 13, if theta increases at a constant rate of 2 radians per minute, at what rate is x, the opposite side to theta, increasing in units per minute when x is equal to 5? Okay, so again, we're going to follow our normal steps, write down what you know, draw your picture, etc. So we're going to draw that picture right now. All right, so we know we have a right triangle. They didn't really tell us which way it's facing. We don't really care, so we're just going to draw ourselves spiffy diffy right triangle. Here we go. They didn't tell us where theta was, right? So we're just going to pick an angle to be theta that's not the right angle. So we're just going to say, theta's over here. And they said the hypotenuse is 13. So hypotenuse is 13. They also said theta is increasing at a constant rate. Okay, right there, that's a derivative, right? Okay, so d theta dt is going to be 2 radians per minute. Okay. At what rate is x, the opposite side to theta, increasing? So x is going to be over here, and they want to know dx dt, what rate is that side increasing when x is equal to 5? So there's kind of my conditions. Okay. All right, so here we go. So if I'm looking at this triangle, I have my hypotenuse, obviously, and I have my opposite side to my angle. So opposite and hypotenuse. What equation can I write with opposite and hypotenuse? Ooh, that would be sine. So the sine of my angle is my, whoops, hello, is the opposite side divided by my hypotenuse. Okay. So in terms of letters, that's sine is my opposite, which is x over my h. Now, I wrote my equation. I need to do a derivative. The derivative of sine of theta, so the derivative of sine is just cosine, but I have to do a d theta dt. I kind of have to do like chain rule here. So derivative of the outside function, derivative of sine is cosine, but derivative of the inside, the derivative of theta is not just one, it's d theta dt. Because remember, we're taking all these derivatives with respect to time. So I got this d theta dt I got to worry about there too. All right, on the right side, I'm going to have to do quotient rule. Okay, so I've got x and h. So I've got, actually, does it tell me that I have a hypotenuse in the right triangle? So the 30, okay, so it's 31 is 38. What's the side? X is 5. Okay, so we've got my f is going to be x, my h is, my g is going to be, my h is going to be g, my g is going to be h. Now, if you do your high D low thing, go feel free. I'd still do f's and g's for quotient. So derivative of x with respect to time is going to be dx dt. Derivative of h with respect to time is dh dt. Okay, multiply on those diagonals and subtract for quotient rule. So f prime times g is h dx dt. Subtract, go the other way, x dh dt. And we're going to divide it by whatever our g squared was, so h squared. Okay, there we go. Now, we know a little bit here, but one thing that we want to point out here is that nowhere in this problem does it tell us that our hypotenuse is changing anywhere. So we're going to make that assumption that dh dt is a constant, that h is a constant 13, which means dh dt is 0. Okay, which is going to help us out a lot. That means that this thing is 0. It's out of here. We don't have to worry about it. All right. So if that's the case, then this is going to get a lot simpler. That means that we know we've got h dx dt over h squared. So one of those h's is actually going to cancel, and we have dx dt divided by h. All right. No problem there. Now, what do we know about, let's see, we know dxdt, or no, we don't know the xdt, but that's fine. That's what we're looking for. We do know d theta dt. We got that. That's 2. We know h. No, yeah, we do know h. H is 13. They told us x is 5. Why did they tell us x is 5? Oh, they told us x is 5 because that's how we're going to get theta. Da da da. Okay. So we need theta. So in order to get theta, specifically, we actually need the cosine of theta. So cosine of theta is, if this is 5, cosine of theta is your adjacent over your hypotenuse, right? Think back to SOHCAHTOA, which means I really need this third side. I need this adjacent side, which we can get. We've got 2 sides. We have 5 and 13. So just do your Pythagorean theorem. 5 squared plus your adjacent squared gives you 13 squared, which means that a squared should be 144, which means a is 12. So your adjacent side should be 12. So your cosine of theta then should be your adjacent, which is 12, over your hypotenuse, which is 13. All right, so that gives you your cosine. So now we can fill in everything we know. Cosine of theta is 12 over 13. Your d theta dt is 2. Your dx dt is what you're looking for. And your h is 13. Okay, cool beans. Slide this up a little bit, and we just got to do some arithmetic. So we have 24 over 13 equals dx dt over 13. Obviously, 13 is going to cancel, so dx dt better be 24. Okay. And in terms of units, I don't think they actually gave us any units on the length. They didn't. They just told us radians per minute. So it's going to be 24 units per minute, I guess. Yep. I hate it when they do that. They really need to give you length. Okay, so dx dt winds up being 24 units per minute on that booger. All right, guys, so interesting little trick problem. Not too bad, really, once you figure out what's going on. But yeah, since they don't tell you anything about the hypotenuse moving, you assume that your angle is changing. So the angle is increasing. The angle is getting bigger. But even though the angle is getting bigger, the hypotenuse length is going to stay the same. That opposite side is just going to get larger for the angle to compensate for the angle getting larger. So your hypotenuse length isn't actually going to change, which means that your dHdt is 0. As long as you recognize that, then the problem becomes a lot more doable. All right, y'all, that's it for related rates. On top optimization.